Okay, section 2, switch input. Introduction to switch inputs. Seems like a very basic topic, but this is not a switch that you're thinking of like a light switch on a wall that's going to directly control something. It's not going to be a switch, and that's basically it. This is not a switch that directly controls anything. When we talk about switch inputs, we're talking about something the computer is going to use as a signal. And I think maybe one of the best examples of a switch input I can think of for you young guys would be your PlayStation controls. Your X, your square, your circle, triangle buttons are switch inputs to that PlayStation controller on what to do. So what you're doing as you're hitting these switches, you're not directly controlling anything. It's just an on-off digital signal that that computer's reading, and it knows by programming what to do with that signal. I have examples of types of switch inputs over here on the right-hand column on page 2, and this is just some of the ones that are on a car. These things are all over the place. There's mechanical and hydraulic type switches right here, and there are electronic type switches. Now, obviously an electronic switch doesn't move. It has no moving parts. You've probably seen the term maybe on a wiring diagram that says solid state. Have any of you ever seen a solid state relay listing on a wiring diagram? What that means is there's no moving parts. Solid state, no moving parts, it's electronic. So we can call them switches. They're really not switches, but they work like a switch, and they will affect a signal voltage the same way as a switch will. Let's think about this for a second. What I'm going to teach you in switch inputs is probably 30 to 40% of inputs on an automotive system. And this would be everything from engine controls, transmission, ABS, body controls, climate control systems, all over the place. We have switch inputs. If you understand the concept of them, you won't need a flow chart to diagnose a switch problem on any system. And just to name some, power steering, pressure, park neutral, transmission range, throttle position. This would be some older designs, primarily used switches, although Toyota continues to use a throttle position switch involved with their throttle position sensor. There's a potentiometer, which is a variable resistor, and then they combine it with a switch. We'll talk more about that later. Headlights, parking light controls, body computer inputs, door lock and unlock, cruise control, windshield wipers, door ajar, climate controls. And then it really gets deep into the car, and that's this bottom section that a lot of our camshaft, crankshaft, vehicle speed sensors operate off of this design, that it's electronic, but it's going to work like a switch. So Hall effects and opticals, and then communication between modules where you have, say, an ignition control module sending a signal to the engine computer for RPM and an injection pulse. It works off of this principle of a switch input. And then, of course, we have some frequency generating devices like mass airflows and map sensors on some vehicles. So that's a lot of stuff, and that's only a fraction of the components on a car that may use a switch input. And I think maybe the best thing that I can do is to show you the difference between a switch that's going to control something and a switch input. Let me just draw you a generic picture. All right, I'm going to draw a door lock circuit, and this isn't going to be exactly how it works, but just to emphasize what we're talking about. A older car may have a door lock circuit that's like this, that the switch directly controls the motor. And I know it's not like this because they're reverse polarity. So I'm not being technical in the drawing that showing a reverse polarity circuit, because this one obviously is switched on the power side all the time. That's not the way door locks work, but this will give you an idea of what I'm talking about. So that switch is directly controlling that motor in this picture. On a switch input design, what you would have maybe to compare is a switch that's going to go into a computer, some type of computer, whether it's a body computer, engine computer, whatever. And this computer is going to control this motor through a relay just because of the high current of the motor. But The difference between these two is this switch right here does not carry any of the current flow that this motor needs. All it is an input to tell this computer what to do with when to turn that motor on and off. Where up here, this switch has to carry all the current flow to that motor. So one of the biggest differences in these two designs and these two switches would be the current flow. The top picture that I'm showing may have, 14 gauge wire going to the switch. And on older door lock assemblies, when you pulled the panel off, they had real heavy gauge wires going to the switches. But today's cars, when you look at the door lock switches, they're real small gauge, maybe 20 gauge wire. And that's because they're switch inputs. They do not carry the current at all. It's just an input to the computer for when to do it. So that would be the biggest difference between a switch that directly controls something and a switch input. I actually have a video on some door lock circuits that I'll show you later on how to control them, how to test them on the switch input side, not the mechanical switch side. Okay, back to the text here. So examples, these are all over the car. Switch inputs. Let's talk about them electrically now. Once we get this down electrically, the designs, then we'll be able to accurately and quickly diagnose any switch input problem on a car. And so there's two main designs. It's pull up and pull down. That's something you want to remember. There's two main design switch inputs. We'll just call them pull up and pull down. Now, I don't know if other people in the industry are using those terms. I do, and I'll show you why as we go. It helps describe the circuit design. Pull up and pull down. It is a digital input. On-off switch is not analog. So for you guys that need a refresher for that, an analog signal would be something like this. It's described as continuously variable. An analog signal, or a digital signal, is exactly that. It's digital and it's on and off. Distinct on-off, no voltage in between. High, low, on-off, digital. So this one's digital, and this one's analog. It is the switch that changes the signal in the circuit. When the switch is open and the switch is closed, that signal is going to go high, low. Very basic concept so far. Okay, page 3. Some generic pictures of switch inputs and what it looks like internal to the computer. Certainly doesn't look like this, but as far as the concept goes and how it works, I think these two pictures emphasize very well. Oh, this is only the pull-down design. My fault. Pull down, the next page, pull up. Okay. So this is the pull-down design, one of two designs in both states, with the switch open, with the switch closed. And I guess we'll start with the bottom left picture. And what we have internal to the computer, which you haven't been exposed to yet, is this 5-volt regulator. This part isn't important for this discussion. It could actually be 12 here. I'm drawing it as a 5. A 12-volt design would just simply be a flat 12 volts coming in on this side, and it would just alter the range. But we'll talk about the 5-volt one since that's the way I have it drawn. Internal to the computer, a 5-volt regulator. You're going to have that on every car. It's basically your low voltage computer sensing circuit. That's your source. It's kind of like the heart of the computer system, that 5-volt regulator. Very, very important piece. But we're just stealing some voltage from that. So this is a constant 5 that I have here. That never changes in this picture. We can think of this voltage sensing circuit, which would be one of these chips. If you looked at the board, it might look something like that. Inside the board, that's going to monitor this circuit. You can think of this voltage sensing circuit as a voltmeter. So this would be your positive lead, and this would be your negative lead of your voltmeter. Does a digital voltmeter support current flow? Most digital voltmeters are rated at 10 mega ohms of impedance. In other words, 10 million ohms of resistance. Is that going to be a path? My question to you is this going to be a path to ground through a 10 million ohm resistor? The answer is no, it's not. So what is this thing? It's just monitoring the circuit. Where is that? It is inside the computer. You don't see it. Computer's monitoring what? Voltage right here is where the computer's monitoring that circuit. We're going to be able to tell what position this switch is in by watching the voltage right there. So a little bit of some laws apply with voltage and voltage drops, and one of them being, well, we have a resistor right here, so resistors are going to drop voltage, correct? But we need to have current flow for that to take place. So right now, there is no current flow in the circuit. That voltage can't go anywhere. That voltage sensing circuit is not a path. And so that whole leg of this circuit reads 5 volts right now. This is if you were out here with a voltmeter to ground, you would read 5 volts on this circuit with the switch in that position. Up here, switch closed. What did the switch close to? It closed to ground. And now this resistor is in play. We now have a drop across this resistor because we now have current flow. The computer's going to read 0 volts right here. If you had a voltmeter out here, you would also read 0 volts. And so we call this design, and it makes sense, a pull-down design switch input. What is the switch doing? It's closing to ground. It's pulling the voltage down. Pull-down switch input. Some truths about this is the signal voltage to the switch is internally sourced by the computer. You can see that the computer is the supply for the switch. With the switch open, signal voltage remains high. When we do the other design, you're going to see that that's opposite. And with the switch closed, this voltage gets pulled to ground. Seems very basic. And it is. But it can be difficult as we add these other designs. Well, there's really only one other design, but I'll tell you where I see guys get mixed up. It's when we start talking about the output side of a car. Right now we're talking about the input side. Let me give you something else that may help you. Some terminology that we're going to need here. When we talk about computer systems, we have wires that come into the computer, and we have wires that come out of the computer. And we'll call these wires that come in inputs, and we'll call these signal wires. Inputs we'll call signal wires. This would be your computer. And then the wires that come out, we'll call these outputs, and we'll call these control wires. Signal wires, we could say the computer is watching. We're watching these circuits. And control wires, obviously in term, is we are controlling. We're going to turn things on, turn things off on the output side. Where I have my guys get confused is when we put section 2, which is what we're talking about, switch inputs, pull up, pull down design, and then we start combining that information when we jump to section 3, which is on the output side where we start turning things on and off, which is power and ground side switching. The terminologies get mixed up very easily. So that's where the confusion really comes in, and we'll try to clarify this as much as possible. But inputs we'll call signal wires, outputs we'll call control wires. Where we're at right now, this is section 2. Section 2 is where we are. When we jump to section 3 next, this is where we're going to be. We're going to be on the output side. And it gets a little bit more confusing, or there's another variable here, is we can actually watch what we're controlling too. And we'll get into that, and that gets a little bit crazy, that the computer actually watches its outputs, very similar to how it watches its inputs. So just remember that with these switches, what we're talking about right now, back to the book here, the computer is not controlling anything in this circuit. Can you guys see that? That the computer is just simply watching this circuit. It has no decision making as far as opening and closing the switch. The computer is simply watching the voltage in the circuit to know the switch position. And let's plug that into maybe the operation of a vehicle. Let's say that's a park neutral switch. The computer wants to know the position of the switch. It's important because maybe it has a rev limiter, and a rev limiter prevents the car from revving past, say, 4,000 RPM when it's in park or neutral. Right? Protects the engine. There's no reason to rev an engine past 4,000 to some of the manufacturers. They put a rev limiter in there, and it won't rev past 4 grand in park or neutral. What do you think may happen if you have a park neutral switch problem? Is going down the road while you're driving, if it reads it's in park or neutral, guess what happens when you hit 4 grand while you're driving down the road? The car goes into a rev limit. I've seen it. I have a case study on it. I'll show it to you later. But that's where knowing the switch input, how it's designed, how it works, how to test it would be key. Just a little perspective on a switch and maybe where it might be used and how it can affect the car. Of course, with this list we have, I mean, you can think of hundreds of symptoms that you might have with a switch input problem. If it's a crank sensor, it's a no start. You know, obviously door locks, they're not going to work. Or maybe going down the road, they just kind of lock and unlock on their own when you hit bumps, things like that. Transmission range and gear position. We have a transmission lockout problem this morning. Of course, that could be an issue too. It's not because yours is grinding, but in any case. All right, next one, next design. This is the pull-up design. And you can see that there's differences here. Oh, wait, I missed something. Back up the page. When this switch opens and closes, the voltage in here is what's changing. This is a constant 5. It never changes. I don't think I mentioned that. That does not change. Let's stay here for a second. I'm sorry about that. Why is this resistor here? We are shorting voltage directly to ground. What would happen if the resistor wasn't there? We would burn this regulator up. Most of your 5-volt regulators can only handle about 1 amp of current flow. They are protected pretty well. The computer in certain vehicles may use some type of positive temperature resistor in there that will protect the circuit. I've seen Chrysler do some different things to protect that regulator for too much current. But in any case, if this resistor was not there, we would overload this 5-volt regulator because you'd be shorting it directly to ground. What does a regulator do is it maintains a constant voltage. If voltage is low, it puts out more current to bring it back up. If voltage is high, it reduces the current to bring it back down. So the resistor is there to protect the regulator. The resistor is also there to cause the voltage drop. So it's key to this circuit. And again, let's exclude this for a second and say that this is actually a 12-volt source. Would the circuit work the same way? Yes, this would be 12 instead of 5. And when the switch would close, it would still be 0. So instead of being a 0 5-volt square wave on off, it would be a 0 12-volt square wave, and you'll see both designs. In fact, you'll see any voltage in between 5 and 12 too. It depends on the car and what their circuit is and how they source the voltage. So I don't want you to think that all pull-down switch inputs are going to read 5 volts. This is just an example. It's a common design. You'll see voltages all over the place. And we have this information further in here about what you want to see and how to test. All right, pull-up design. Notice that it is externally sourced in this one. So we have 12 volts outside. I didn't draw a fuse in the circuit. Some of these are electronic, so there is no fuse right there, but I just left it basic. Externally sourced, internally grounded, and notice the difference now. With the switch open, there's no voltage here at all. So the computer's going to read 0 volts, just 0 here with the switch open. Switch closed, this is going to be 12. Computer reads 12. Pull up design. So it's opposite. Look, switch open, signal voltage is low. Let's back up a page. Switch open, signal voltage is high. So you can see that they're opposite of each other in operation. If you were to draw it in a square wave, this would be on and this would be off on this design. Switch is on when the voltage is high, switch is off when the voltage is low. Page 3. This is on and this is off. So they're opposite of each other. So pretty basic so far, right? It's a little bit different when you see them on the car. You see them on the car, it's a lot more difficult to identify circuit design on the car, and I'm going to show you how to do that. So what we want to do first, before troubleshooting these, because I have a real good step-by-step on troubleshooting these as we continue here, but what we want to do primarily is we want to identify what we have first. If we can identify circuit design, then it's much easier to troubleshoot, and you won't have to be tied to that engineer written flowchart that's never designed for speed. So circuit identification, of course, is next. We need to identify the circuit. Once we identify the circuit, then we can troubleshoot it. So there's two ways to identify. Remember these two ways. Number one, we can use a wiring diagram. The wiring diagram, though, is limited in identification to the mechanical and hydraulic type. So one of the things about circuit identification when it comes to switch inputs, because we also mentioned in page 2 that there are electronic switch inputs. We cannot identify circuit design on these using a wiring diagram in most cases. And the reason why is they just draw, say, a crank sensor, the wiring, and computer, and you don't know what's what. In other words, here's your crank sensor, here's your computer, there are 3 wires. Yeah, the diagram may list power, ground, and signal, but you can't know if the signals pull up or pull down by the diagram because there's no other way to identify that. You have to know the car. So electronic ones we can't identify with a wiring diagram. I'll show you more electronic circuit design later and how we can identify that. For this identification discussion, we're just talking about mechanical and hydraulic type. So look at the wiring diagram. Use a voltmeter. Starting with the wiring diagram, it's as simple as look at the switch and follow the wire that doesn't go to the computer. Wiring diagram right here. This is on a VTEC oil pressure switch on a Honda. And I actually have a video on this. You guys can watch this later. We were doing some VTEC solenoid testing. Part of the test was checking the switch. And this VTEC oil pressure switch, its job was to tell the computer when the VTEC solenoid operates that there's hydraulic pressure change. And if the computer sees a hydraulic pressure change by the switch closing, so the hydraulic pressure, that passage, when that solenoid would turn on, oil pressure would close the switch, that would tell the computer that that VTEC circuit is working properly. It's used for feedback, it's diagnostic purpose. So that's what it's there for. As you can see in this picture, what I'm telling you in the circuit identification, understand this. You can't see this. I drew that in there. All you see on a wiring diagram is some letters and a wire that goes to it. And it said VTEC oil pressure switch. You don't know if it's pull up or pull down. What's the key then? The signal wire is not going to identify it, ever. It goes from the switch, that's what I have highlighted in yellow here. It goes from the switch to the computer. You don't know what it is. But check this out right here. It's hard to see. Maybe you guys can see it. It is a ground symbol. So being externally grounded tells you what about the switch input? What design is it? Yeah, this is a pull-down design circuit. This is a pull-down design. We'll do the video later. I want to concentrate on identification so you guys get an idea. Let's go back up so you have a little bit more perspective here. On the pull-down design that I have here, again, where is the wire going that doesn't go to the computer? And on the pull-up, where is it going? So do you see how you identify those? What would this look like, though? It's not going to say 12 volts on a wiring diagram. What would be 12 volts? One of these things. See a fuse? What is that? That's the positive side of the circuit. Okay? So circuit design, you follow the wire. You want to remember this. Without a voltmeter, using a wiring diagram, what do? Follow the wire that does not go to the computer. If it goes to a ground, it's a pull down. If it goes to a power, it's a pull up. So that's identification number 1. Number two, we can actually identify a switch input using a voltmeter. There are some variables to this test because if the switch already has a problem, if the circuit already has a problem, let's say the signal wire shorted to ground or something like that, it might make identification impossible with the voltmeter. You won't know circuit design without the wiring diagram. So I'm not saying this is 100%, but it does work. It is accurate. And what we're going to do is check voltage levels on both sides of the switch. Force the switch to close. Close is going to be the key. Figure 1. This is actually on page 9. Don't turn there yet. I want to do something else first. Let's go back. If you're working on the car, you don't see the whole circuit. What do you see at a switch when you're working on the car? What you might see is a component, a connector, 2-pin connector, and that's your switch. That's what you see on the car. So it's not going to be like left and right. You don't know where the computer's at. And let's say you see this circuit and you read 12 here and 0 here. Do you know the circuit design yet? At 12 and 0. You don't. Let's say we activate the switch, and here we'll do 2 different ones. And we read 12 and 0 again. This would be both designs, and I'm drawing them this way intentionally just to have you think a little bit. This would be with the switches off. Both designs are going to look the same. You don't know which wire is which. You don't have the wiring diagram in front of you. That's the point, and that's why I drew the wires, the voltage, the same on both. When you turn the switch on, or when you close the switch, this one is 0 and 0, and this one is 12 and 12. The switch is closed. Now can you tell me circuit design? The one to the left is what? The one to the left is a pull-up design. And the one to the right is a pull-down design. Can you tell me which one the signal wire is in these 2 pictures? This is the signal wire, right? It changes. That's the signal wire, the changing one. Okay, so I'm trying to illustrate that in these figures, so let's take a look at what I have in the book now. Force the switch to close. You guys understand that identification truly comes when the switch is closed. With the switch open in my picture, didn't both designs look the same? Now, granted, you could make the argument that you need the switch open and closed to identify it, but it is really the closed position that identifies this with a voltmeter. Okay? Closed position identifies the circuit design with a voltmeter. So let's go down to figure 1 first. Let's look at the pull down. And now I have the computer in here, so it gets the visual a little bit better on what I just drew and why it looks like that. So imagine that you're on the car and your perspective is only this right here. That's what I just did for you guys. I left this out of there just to challenge you a little bit to think. But that's all you see. What's in that green box is all you see. You can't see the whole circuit if you're trying to identify it with a voltmeter. You just see 2 wires and a switch. This is what it looks like. This is why it looks like that. Internal to the computer, if you wanted to add this, you'd have a resistor and you'd have a source. In our case, this time it's 12 volts, and you'd have some type of voltage sensing circuit inside of that computer. That's what that would look like. I left it out of there intentionally this time because when you get to real wiring diagrams, this isn't there. You need to be able to visualize what's inside that computer. So 12 volt. Again, we have a resistor with no current flow. There's no voltage drop. So if my source is 12, even though I may have a 100,000 ohm resistor, it's still going to be 12 volts on the other side of that. There is no voltage drop. I don't care what that resistor is if there's no current flow. So 12 on the other side, 12 all the way out here. You close this. We close this up here. This drops to 0 volts. This drops to 0. Our resistor is now in play, and it's dropping all the voltage in that circuit. So identification with the voltmeter, it went from high voltage to low voltage when the switch closed. Pull down design. That was page 9 for you guys following. I'm going back. Page 5, you guys can just go to the next page. Pull up switch will show high volts on both wires with the switch closed. Let's go to figure 8. Pull up design input, normal operation. This is what the circuit looks like. And again, on the car, let's say that all you're going to see is this much info. And you see with the switch closed, that's truly what identifies it. Switch open, they were both reading 12 and 0. And I know what you might be thinking is, well, with the switch open on the other design, wasn't this one 12 and this one 0? So they were opposite that way. But on the car, is there a left and right? Well, that wire's going left. Have you ever thought that looking at a connector? No. I can't see which way that wire is going, and that's why I'm challenging you that way. Don't look at this picture and say, well, the pull-down design had 12 volts on this side and 0 on this side, or the pull-up has 12 on this side. They're opposite, 0 on this side. You can't do that on the car. On the paper up here, you can, but if you're saying that up here, you're identifying the circuit with a wiring diagram, and that's what we're trying to not do. Let's say you're working in your backyard, you don't have a wiring diagram, and your door locks aren't working right, and you need to figure out circuit design before you can test it, so you understand the perspective. All we have is a voltmeter. We don't have a wiring diagram. We can still do it. Pull up circuit design. So close the switch was key. Okay? Remember this to help you out. That signal wire is always the wire that changes. This is the one that changes when the switch is open and closed. And then I already described this. Both designs with either the switch open or the connector unplugged will read high volts on one wire and 0 volts on the other. And identification can only be done with a wiring diagram if you had a problem with that switch and you couldn't close it. You would need a diagram to know. And then on the diagram, of course, we can tell using the diagram combined with our voltmeter, we can figure out which one's which. And that's down here, switch unplugged, signal wire voltage is high, switch unplugged, signal wire voltage is low. And you can see that in these figures. I'll do it. Don't flip your pages. Figure 1. Signal voltage, if you can picture this circuit, let's say with a dead switch or it's unplugged, what are we going to read on the signal wire? We're going to read 12 volts here all the time on the signal. On the pull-down design, where the pull-up design, unplugged, bad switch, you're going to read 0 volts here all the time. So you can see that using the diagram combined with a voltmeter, you can figure out which one your signal wire is. Okay, so identification, again, is key. Before we can do troubleshooting on these, we need to identify the circuit.